Hello, this is Jack Jackson, and we're back with our next in our series of videos introducing and explaining and working with hypothesis test. We've chosen to use a z-test, a one-sample z-test, as our way of introducing this. Now, this is a test for doing inferences about population means based on a sample mean. So in this video, in this section, we will work through an example of a one-sample, two-tailed z-test. In this example, we'll be given a data set for a sample, and we will work out the appropriate hypothesis test. This will follow closely the methods of the previous slides very closely, and we will go through both the critical value method and the p-value method here. So here's our problem, our real-world setup here. In 2005, in a report, it would determine that the mean amount of television watched by Americans was 4.55 hours per day, with a standard deviation of 2.31 hours. We want to test if the amount of television watched by Americans now is different than this. So we would assume that maybe it's no difference. So our null hypothesis is that it hasn't changed, right? That the people are still watching 4.55 hours a day, okay? And we have this population standard deviation of 2.31. So what could we do? Particularly if we want to try to prove something else, we assume the null hypothesis of a 4.55, the traditional amount. So what we could do is go out and take a random sample of Americans and determine the following amount of television per day for each person sampled, and we have the first person is 1 hour, the next one is 4.6 hours, and so forth. So now we want to perform a test of hypothesis to determine if the current amount of television watched by Americans is different today than in 2005, and let's use an alpha level of 0.1, 10%. Well, first of all, we got to figure out what's appropriate. We note that a one-sample, two-tailed z-test is appropriate because we're testing for a difference in mean between a single sample and a hypothesized population. It's two-tailed because we're concerned with any difference in mean, including either an increase or decrease. And you got to look for keywords right here. See, it says different today. If it said less today than in 2005, it'd be left-tailed. If it said more today than 2005, it would have been right-tailed. But since it says different today, different could be more or less. So it's a two-tailed test. The distribution of individuals is normal, so the distribution of sample means is also normal. See the normally distributed right there? So it doesn't matter how many we have here. The population standard deviation is known. It is 2.31. So this is all the conditions that we need for a one-sample, two-tailed z-test. So what do we need to do? Well, we put this data in, and I'm going to put it in L1 in my calculator. This is a TI-84. You can do the similar thing in a TI-Inspire. And we put our data in a list or in a spreadsheet on the Inspire. We go to calculate one variable statistics, and it returns this. There's actually two things we need to know from this, and only two things. We need to know the sample size, so it counts them for you. There are 20 of them. Of course, we could very easily count it by hand to see there are 20. And it finds the mean, 4.735. Of course, we could have just added those up and divided by 20, even with a very simple calculator or even by hand, and we would have gotten 4.735. So those are the two things we really need from that. Okay, so let's just remember, we started here by typing the data from the given sample in our list. A couple things, don't forget to first clear the list. You do that by putting your cursor on L1, hit clear, and then enter to clear this out empty. And then type in the list, type in the 1, enter, 4.6, enter, and so forth till you get it all in there. After it's all typed in, we get out of this by doing quit, which is second mode. We get to this screen here in the middle by pressing Stat and then right arrow to calc, choose number 1, hit 1, or just hit enter there, and then you tell it list 1. So you have to put in L1, which is second 1, and then it returns this stuff, and it returned a lot of stuff we didn't need. All we really need was X bar and N. Okay, so again, since we're talking about different today, we're talking about a two-tailed test. The alternative hypothesis is mu is not equal to 4.55. The null hypothesis is that mu equals 4.55. We have the sample size of 20. Sigma of the x's, the original standard deviation of individuals, is 2.31. The sample statistic is 4.735. Notice that 4.735 is bigger than 4.55, but we wouldn't expect it to be exactly the same. The question is it enough different that we can conclude that people are really doing watching a different amount of television than in the past? Now, if we want to use the critical value method, we need to compute the test statistic, which is just a z-score of the sample mean under the assumption that the null hypothesis is true. So we need to take the X bar value, which is 4.735, minus the hypothesized mean. According to the null hypothesis, that's 4.55. We divide by the standard deviation, but this is the standard deviation of the X bar values, which is standard deviation of individuals divided by square root of n. So that's sigma divided by square root of n, 2.31 divided by square root of 20. That's all in the denominator. Work all that out, and you get 0.3581. Here you can see part of a calculator screen with the same thing. That's our test statistic. In the calculator, I even stored it as z, so I wouldn't have to type all these digits in again. So now at this point, we actually have two different methods. We'll first illustrate the critical value method. We need to find the critical values corresponding to the alpha level we were given. We were given an alpha level of 0.1. Since this is two-tailed test, the probability below the lower critical value is only half of alpha, which would be 0.05, and above the top critical value, or upper critical value, is also 0.05, half of alpha. Okay, so let's figure that out. We can do that with the inverse norm. So that's just an inverse norm of alpha over 2. Alpha over 2 is 0.05, and that is a standard normal, 0, 1 there. 0 mean, standard deviation 1. When you do that inverse norm, you get negative 1.644. The upper critical value is just the opposite of that, since this is talking about z-scores, which are centered on the mean of 0. And then you compare the test statistic, which was also a z-score, 0.358, and notice it is between these two critical values. So it is in the do not reject region. There's not enough evidence to reject the null hypothesis. We do not have enough evidence to say that people watch any television any differently than they did in 2005. The p-value method, we can compute it either from the test statistic, the z, or z star, or we can compute it right from the X bar value. Either way, it's a normal CDF, but it is going to be twice that because the p-value is in both the left tail and the right tail, and we need to add those two together. So that's going to be, and they're the same size, so we just double it up. So it's 2 times the normal CDF from z star to infinity. So that's 2 times normal CDF. There's the z value there. And then we can go, remember I told you for a standard normal, just use 10 for instead of infinity. That's plenty big enough for when it's 0, 1 here. Or we could do it directly from the X bar values and not even have to find out a z-score at all. If we do that, that's 2 times normal CDF. You put in the mean here of the sample, and then here you put in the hypothesized mean plus 10 times the standard deviation, or some other number that's maybe just a little bigger than that. And then you give it the mean and standard deviation. Now that standard deviation, once again, is the standard deviation of the individuals divided by square root of sample size. That's the standard deviation of the X bar values, sometimes called the standard error of the mean. Well, either way, whichever one of these calculations you do, you get the same answer, and there it is. Here in the calculator I did it the first way, and at the beginning and down at the bottom I did it the second way. Okay. And let's see what we've got here. So anyway, that's what we got, 0.72. Now that's a big p-value. That's way bigger than alpha, so we definitely do not have enough evidence to reject the null hypothesis. Okay, so once again, here's a visual illustration of the critical value method and the p-value method. The top with the red graphs, red shaded area in the graph, is the critical value method. The red region is the alpha, which is 0.1, split into half of that in each tail, 0.05 in each tail. Alpha is 10%, each tail has 5%. And the boundaries of that are our critical values, which we figured out a while ago is negative 1.64 and positive 1.64. Our Z star value was about 0.36, which is clearly pretty darn close to the mean. It is in that non-reject region, that unshaded region. So the red is the alpha, and then we compare whether the X bar value lands in there or not, or in this case the Z score of that. Down here in the bottom one illustrates the p-value method. The total blue area is the p-value, which has an area of p over 2 in each tail. Notice that the boundary of one tail of the blue region is our test statistic, Z star right here, and then you just get that to the right, and then a corresponding mirror image of that on the left, and we add up all that blue area. That's the probability of getting a result this extreme, this or more extreme, if the null hypothesis is true, and there's a really good probability that could happen, and that is about 72%. So there's not enough evidence to reject the null hypothesis, so we do not have evidence that people are watching TV any more or less than they were in 2005. When we finish this part of the test, we're not completely finished until we state our conclusion. And our conclusion needs to be stated in a sentence or two. This conclusion should be phrased in the context of the original problem. It should include the type of test used. It should include the p-value, the alpha value, and the conclusion stated in the context of the problem. So let's look at an example of how we might say this. So this was our the blue text up at the top is our original problem. Let's read the red down here. Notice that we state the final conclusion in a sentence or two. This conclusion should be phrased in the context of the original problem. It should include the type of test used, the p-value, and the alpha value. Let's see if my statement does that. The mean time spent watching television by the individuals in this sample is 44.735 hours. With a p-value of 0.72 and alpha equals 0.1 from a two-tailed z-test, there is not enough evidence to support the conclusion that the average time spent watching TV has changed since 2005. So note that although the mean of the sample is higher than the hypothesized mean, this difference is not large enough for us to conclude that the mean of the population has actually changed. A sample such as this is very likely, 72% likely, that we would get this or something more extreme, if the mean is still at the same 4.55 hours per day as stated. Let's do another exercise in the next video, which is a right-tailed exercise.